again to the cloud. Right. So number one, well, numbers 1 and 2, kind of along the same lines of what we were talking about last class, where you're asked to create a graph and then find the limit graphically, right? Or find limits graphically, as in the case of the second problem. So I'm going to type in my function f of x equals division 2 over x plus 3. See what the graph looks like. It doesn't have to be a perfect graph. It just has to give you a sense of what's happening around the limiting constant, which in this case is x equals -3. All right, so that's my limiting constant. I'm going to make it dashed, so it pops off the page a little bit. Get a little screen grab action going on here. And then just pop it in so I can mark it up. All right, something like that. All right, a little out of whack, but not the end of the world. All right, so what we're asked to do is determine what's happening as we approach -3 from the left. So I'm moving my point closer and closer to the x value of -3. You see the x value is decreasing, decreasing, decreasing. And it's just a question of, as I get closer and closer to the x value of -3 from the left, where's y going? If I follow the graph, you see that it seems to be going down forever. So that's an indication of -infinity. All right. If I want to come in from the right, which is the second question, -3, that little plus sign means you're coming in from the right. My x value is decreasing, 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 getting closer and closer to the x value of -3. As it gets closer and closer to the x value of -3, the y value it's approaching seems to be, and just follow the trend, it appears to be positive infinity. Since the two limits do not equal one another, all right, these two are not equal, we would say the limit does not exist. All right, there's a contradiction. Whenever that happens, it means the limit does not exist. Right. In number 2, it's basically a 2-for-1 kind of question. All right, so I'll type in the function x minus 3 up top, then x squared minus 2x minus 3 on the bottom, back to the standard zoom. It's asking us to approach -1 from the left, from the right, and then overall. But then it's also asking us to approach the x value of +3. So I'll put that in also. All right. So in the case of -1, and again, I'll just do the screen grab and pull it in there so we can have it. Nice looking graph. All right. So as we come in from the left, approaching a -1, right? So the key here is that we're approaching the -1, but from the left, we're following the curve. As I get closer and closer to the x value of -1, it seems that it's another instance where I'm going down forever. All right, down forever is represented by a -infinity. From the right, as I get closer and closer to the x value of -1, it appears that it's another case where I'm going up forever. Up forever is represented by a positive infinity. These two are not equal to one another. So the limit as x approaches -1 has a contradiction, and so we would say DNE does not exist. All right. But then we kind of look at this as part 2 of a question, or of the question, and say now we're focusing on the x value of -3. All right. So, oops, start trying to drag a point on the wrong graph. So as I go from the left to the right, approaching the x value of +3, it appears that I'm approaching this open circle, whatever this is. All right. So this is really an open circle situation. It's just a matter of figuring out what y value that corresponds to or corresponds with. Grammar is not my strong point, as you've seen. All right. So I want to know what this y value is. So there's a couple of ways to handle that. One, try to ballpark it and see if it kind of locks in on something reasonable. So as I get closer and closer to the x value of 3, it seems that the y value I'm getting closer and closer to is in that 0.25 interval. You know, something around, 0.25, 0.26, 0.27. All right. So it's just a question of which one is it, so we can bring it in, zoom in substantially. And if you do that, you see that the markings on the left side of Desmos that says 0.25, that lines up perfectly with the intersection between the dashed vertical line and the curve. All right. But if I'm unsure, I can still kind of keep bringing it in. And I'll be able to see that I'm really getting closer and closer to 0.25. All right. Bring it in further if you want, like as much as it'll let you. Well, it stops giving you points, but it's pretty clear that this is at 0.25. All right. If you just kind of line it up, you see that it's at 0.25. So I'm pretty confident about that. All right. We can figure it out algebraically. I'll take a look at that in a second. But for now, I'm inclined to say that from the left, we're approaching this point. From the right, we're approaching the same point, and that point has the value of 0.25. All right. Because we're approaching the same number, 0.25 from the left and from the right, our limit overall would be 0.25, right? Or 1/4 if you want, right? But let me just show you really quickly how you take care of this algebraically, right? What you would do is factor anything that's factorable, in this case, just the denominator, x minus 3x plus 1. All right. We have a common factor that would cancel away. So what we have is a simplified expression that we would call y equals 1 over x plus 1. All right. We know that there's a hole at x equals 3 for a couple of reasons. One, because that is the location of the discontinuity on the graph. The other is, if we were to take our common factor, x minus 3 over x minus 3, instead of equal to 0 and solve, you get x minus 3 equals 0, giving x equals 3. That's the location of the hole. All right. So we would then just evaluate y for when x is equal to 3, and you get 1 over 3 plus 1, which is 1/4. So the hole is at 3, 1/4. All right. So that's an analytic way of getting to that same value. All right. We were confident that it was 1/4, but you can never be too sure, right? So quick double check goes a long way. All right. So let me take a second and show you this on the TI. So on the TI, the way I handle it is it's maybe not as straightforward as it could be, but it gets the job done, and it gets the job done well, and that's the important thing. So what we do is we put in the original function. This is the other thing. X minus 3. You could use the fraction tool if you want, alpha y equals, and type it in that way, but I already started doing it this way. So minus 2x minus 3. All right. Then you would go to the table and look for any discontinuities. All right. So the table, second graph, brings up the table. Oops, I hit the wrong thing. Second graph brings up the table. Look for any discontinuities. You'll get an error message on a handheld TI. This one just says NA. All right, you see an NA at 3 and an NA at -1. All right, little issue with this is that if the discontinuity was not a whole number, it wouldn't necessarily show up in the table without you investigating further. All right, but then you take a look at the graph, zoom 6 to get your standard viewing window. You know what, I'll just put the window in myself. Clear, -10. And you see something that looks like this, showing an asymptote at -1, but not showing an asymptote at x equals 3. But you know there's a discontinuity there, and it's not a jump, so it must be a hole by process of elimination. I mean, I suppose it could also be an oscillating discontinuity, but the more experience you get, the more you realize how unlikely that is. You could zoom in a lot and see whether or not it actually goes to an oscillating function. But I can tell you right now that the only way there's going to be an oscillating discontinuity is if you're dealing with an oscillating function to begin with, like a trig function or something along those lines. All right. So at this point, you would now say, okay, so I know there's a hole at 3. I don't know what the y value is. So what you would do is go through the algebraic process to some extent, stopping at the simplified function. Then you go back into y equals and type in that simplified function, 1 over x plus 1. Then go back to the table and do a comparison. All right. So you see at -1, it's still NA. That's because the original function had an asymptote at x equals -1, and so does the simplified function. Now, at 3, on the other hand, the original function had a discontinuity at 3, but the simplified function does not have a discontinuity at 3. It has a solid point because we've removed that discontinuity, showing that that solid point has a value of 0.25. Now, if you graph them both, you see that you only get one graph. They're the same, right? One's overlapping the other, right? So that's telling us that the original function had a hole in it. The new function filled in that hole, filled in the hole specifically at the coordinates 3,1 quarter. All right. So that's the TI way of going about it. It's, you know, it's almost apples and oranges because it's so different in terms of how you manipulate the two different types of calculators, but essentially they're giving you the same thing, just in a much different way. So the next page has some pre-printed graphs on it. These are a little bit more user-friendly because you're not relying on technology to create the graph for you. You're relying on your ability to analyze the graph once you have it created for you. All right. So looking at the questions here, you see here the overarching instructions say, given the value of C, use the graph of F to find each of the following values. All right, so it's telling us to find F of C, but then in this problem, it tells us that C is equal to 2. All right, so part A is really saying find F of 2. B is saying find the limit, instead of as x approaches C from the left, saying x approaches 2 from the left of the function f of x. This is the function f of x, this whole thing here. All right. C is telling us to do the same thing, just coming in from the right. And D is telling us to draw a conclusion based on the relationship between B and C. All right. So f of 2, that's not calculus. I mean, it's the form of pre-calculus, but it's even before that. It's in you learn that first in an algebra class. It's saying what is y when the x value is equal to 2. All right. So what we do is we go to the graph, we look for the x value of 2. We go up and down the graph and look for a solid point. There is no solid point. There's only an open circle. So there's no solution here. There's no value that exists when x is equal to 2 on the graph. All right. But if we come in from the left, we can find a point, a location, a y value that we're approaching as x gets closer and closer to 2. So right now I'm at an x value of -3, -2, -1, 0, 1, 1.5, 1 3/4, and so on. As I get closer and closer to the x value of 2, the y value I'm getting closer and closer to is whatever the y value is at the hole. All right, that y value would be 2. So that's my limit coming in from the left. Coming in from the right, start on the right-hand side, follow the path. I'm just asking what y value am I aiming for as I get closer and closer to the x value of 2 from the right. I'm aiming for the same location, which has a y value of 2. Remember, with a limit, I don't actually have to get there. Right? I just have to be aiming for the spot. All right. If my analogy was the black hole, you know, like the event horizon, that's the open circle. You'll never actually get to the black hole without being destroyed first, you know, gravitational forces and all that. So that's really what's happening here. We're just saying we're aiming for that spot. We're never going to get there, but that's what we're aiming for. You know, it's the same thing. Like you use the sun as an example. You're in a spaceship and you're flying. You're aiming your ship towards the sun. You're never actually going to get to the sun before you blow up, but that's what you're aiming for. Right? That's what a limit's talking about, what you're aiming for. And so since these two are equal to one another, these are equal, that's what our limit is. All right, our limit is equal to 2. All right. So the next one is the same, really the same question. The C value is still a 2, but we're going to get different answers here. So let me wipe out this stuff. So it's saying, what is the point that exists at the x value of 2? Well, there is a solid point there. At the x value of 2, there is a solid point. It's right here at the y value of 3. All right. Coming in from the left. So starting on the left, working my way up the path, as I get closer and closer to the x value of 2, I'm aiming for this open circle. All right, I'm aiming for that open circle, which has a y value of 4. So that's my limit coming in from the left. Coming in from the right, I'm following the path and getting closer and closer to the x value of 2. I'm aiming for this open circle, which has a y value of 2. These two limits are not equal, so the limit as x approaches 2 of the function f of x does not exist. All right? There's a disagreement. There, from the left, from the right, you're not aiming for the same point. All right? So these are showing discontinuous situations. So I'll tell you right now, in order for a function to be continuous, all of these answers need to be the same. All right, all of these. All right, A, B, C, and D. That's actually how you determine if a function is continuous. You determine based off of the limit from the left, the limit from the right, and whether actually a point exists at that location. We'll talk more about examples related to that in a couple of minutes. C approaches -2, or X approaches -2, I should say. Let me, I'm gonna get a little creative here. copy, paste. And I'll leave the sides the way it is. Bring it in, these should be negatives now. Oops, and stray mark. All right, so we're approaching -2 now. So we look at the graph again at -2. Sorry, I almost tripped myself up. -2 is the key number here. All right, so all of this stuff here is irrelevant. All right, I'll actually make a note of that. This is a trick question. And I've been using this trick question for years, and I almost tricked myself on my own trick question. Right, so that's just who I am. Right, so this is irrelevant because the point of interest is over here. We're interested in the x value as it's approaching -2, not +2. Right, so I'll take my point wherever I put it. Come on down here. Take my point, bring it in from the left-hand side the left-hand side. As I approach this location, I'm approaching this point here. All right, now the first question is asking us what the y value is at that location is 0. What am I approaching? I'm approaching that solid point from the left and from the right. So from the left, I'm approaching this location. From the right, I'm approaching that same location, all of which have a y value of 0. So these are the same, and so therefore the limit as x approaches -2 is equal to 0. And what this tells me, we just kind of proved or justified anyway that f of x is continuous at x equals -2. I don't know what that means. I've never done that before. So, okay. So the last one is saying we're going and approaching an x value or c equals 3. So we're approaching an x value of 3 from the left, from the right, and overall. So I'm just going to write f of 3. I'll rewrite it here. Limit as x approaches 3 from the left of the function. Limit as x approaches 3 from the right of the function. And the limit as x approaches 3 overall of the function. So again, the location of interest, I'll use a highlighter here, already a dashed line there. From the left and from the right, we're approaching infinity. Right, we're going uphill forever. Right, there is no point when x is equal to 3. It's an asymptote. So we have no solution for this. We're going to infinity from the left and from the right. So the limit would be infinity, but we wouldn't have continuity because there isn't actually a point that exists there. Right.